Hello, thank you for tuning in to our webinar. Today, I'm going to be talking about IoT gateway frameworks using Intel hardware and AWS. My name is Martin Kronberg. I am a technical evangelist over here at Intel, and I've been working with this technology for about 6 months now, and I've been running workshops, doing all kinds of developer engagements, and I'm really excited to share some of the stuff that I've learned with you guys today. So to start off with, I just kind of want to give a overview of the Intel gateway solutions, as well as kind of where Intel exists within the IoT space in general. So to kind of give a high-level overview of IoT architectures, you can start at one end looking at endpoints or things or whatever you want to call them, but essentially sensors and actuators that will take readings from the environment and also have some kind of effect on the environment. So an example could be a thermometer, right, that measures the temperature in a room, and then it is linked to a smart HVAC system that brings the temperature up and down. Now, on the other end of that IoT architecture is cloud-based analytics. And this is where a lot of those really interesting IoT applications arise from. So you have things like machine learning, you have things like predictive maintenance, big data processing, uh, a lot of growing and really interesting fields, which will kind of take that data and turn it into business logic or some kind of usable form. And now, in order to get from those sensors to that cloud-based analytics, we need a couple of steps. And this is kind of where Intel comes in terms of the IoT space. And what we have are gateways. Now, a gateway is basically a device which will gather the sensor data. It's going to package that sensor data, do any kind of pre-processing, clean it up, do any kind of noise filtering, things like that. And then it will send that data off to the cloud. And it will do so in a secure way because you can store certificates or any other kind of authentication methods on the gateway. So that's the traditional IoT framework. And what we're going to be talking about today as well is introducing a new layer through AWS Greengrass or a fog type solution. And I'll get into that more later, but just keep in mind that this is something that's going to be running on the gateway itself as well. So specifically when I talk about Intel gateways, I'm going to be referring to a NUC gateway. So a NUC is a so-called next unit of computing, which is a term that was coined by Intel, and it refers to a series of smaller customizable PCs which come in a really wide range of specifications. And these specifications range from really lightweight prototype devices meant for a simple smart home system, for instance, all the way up to a hardened commercial grade device that has industrial I/O and is running on the latest generation i7 processor. So that wide range of compute basically means that you can fine tune your edge compute system to be just the right balance between your power requirements, any kind of heat that the device might generate, the cost of the device, as well as the processing power of the device. And since all of these gateways run on the same x86 architecture, you can shift from one platform to another without really having to worry about architecture compatibility. So everything that we do here at Intel with IoT is based off of open source technology. So all of our libraries, all of the code samples that we have for developers, and as well as the operating system itself is going to be all open source. For instance, on the gateway that I'm going to be showing the demo on later today, we're running Ubuntu 16.04. And we're leveraging the Emra library in order to actually read the sensor data. So, Ubuntu is a pretty familiar OS to anyone that's developed on Linux. And Emra specifically is a sensor library developed by Intel. And I'm going to talk a little bit more about that in a moment. But basically, in short, having an open source technology ecosystem means that you're going to have better interoperability because you can work with other open standards easily. And also, it means that when you're developing your project, you can pull whatever pieces of code you want and use it freely without having to worry about licensing or anything like that. So I mentioned Emra in the last slide, and I just want to kind of dive into it a little bit deeper here. So Emra is a C++ library that has bindings for both JavaScript, Python, as well as Java. And it's used to control low-level sensor functionality. So what this basically means is that you can access GPIOs, you can read-write to an I2C bus, or interface with a microcontroller board over Fermata, amongst other low-level interactions. I also mentioned interoperability earlier. Well, you can use Emra across a huge range of platforms. So, all of the gateway stuff, obviously, Intel NUCs, upboards, minoboards, any other Intel microcontroller. But Emra will also work on non-Intel boards like the Raspberry Pi, BeagleBone, even some FPGAs based off of Altera chips. And what this basically means to you as a developer is that you're not limited to hardware. You can develop on any hardware that you have available right now. And then if you decide to shift over to Intel-based platform, you can do so and keep all of your same sensor code if you use Emra. Now, having all these low-level libraries is great, but also as a developer, it's really nice to have access to higher-level APIs. And that's where UPM, or the Useful Packages and Modules library, comes in. UPM is built on top of Emra and is a high-level API sensor library with support for over 400 different sensors and actuators. So these sensors are things like temperature sensors, moisture sensors, accelerometers, Hall effect sensors, as well as actuators like stepper motors, LCD displays, or just a simple relay. So these sensors also range from simple prototype sensors all the way up to more industrial grade sensors. So basically, by using UPM, you can develop a proof of concept very quickly and easily using prototype sensors, and then shift your project over to using more industrial grade sensors while keeping the same framework. You would basically just have to pull in different library modules for different sensors. So if you want to kind of start developing using the Intel IoT ecosystem, we have developer kits that basically give you a gateway platform as well as a pretty basic sensor package where you can sort of start plugging things in, start building a proof of concept. And we have a lot of code out there that sort of utilizes this kit and shows off how you can build a proof of concept in a lot of different verticals. So retail, smart industry, things like that. And this kit's really great for learning about the ecosystem and building some of these projects. And the demo that we're going to be looking at today is built using this kit. So finally, to tie all this up together, Intel has created a hub for IoT developers at software.intel.com/IoT. Here you can find the software that I talked about, the hardware specifications. You can find IDEs. You can find community forums. You can even find market research about different verticals in the IoT space. and a lot more. So, if you want to start learning more about developing IoT projects with Intel, I would definitely recommend starting here. Okay, so that was a quick overview of Intel IoT, and I want to also do an overview of AWS IoT. So AWS, or Amazon Web Services, has become ubiquitous in modern cloud computing. AWS provides compute servers, storage space, and many on-demand software as a service for developers looking to utilize the so-called serverless computing model. So one part of this massive system of services is AWS IoT. And AWS IoT is a collection of services that allows the developer to do a number of really useful things in IoT. So first of all, if you look at a gateway, it is the device that you're going to gather data from. So in our case, it's going to be the Intel NUC. So this gateway will have some device SDK running on it, which will basically allow it to connect to AWS IoT services. One of those services is going to be authentication. So we're going to authenticate the connection to AWS IoT using a system of certificates. Another service that AWS IoT uses is the so-called rules engine, which basically allows you to redirect your data from the device gateway to any of the other AWS services like Lambda or Elasticsearch. There is also a component of AWS IoT called the Thing Shadow. And the Thing Shadow is essentially a way of storing the device state of what's happening on your device, as well as being able to interface it with any kind of control application. So sending commands down to the device. And all of this is tied together in the AWS IoT API, and as well as having all of these things in a general registry. So overall, that is the AWS IoT framework. So when we talk about the AWS IoT services passing data back and forth, it uses two basic concepts. So one, MQTT, or Machine Query Telemetry Transport, which is a publisher-subscriber communication protocol, and it's becoming a standard in IoT at this point. And it essentially relies on a broker or server receiving messages from a publisher and then sending messages on to any subscribers. It's based around publishing and subscribing to specific topics, which are created by simply sending a message to a topic. So this broker exists as an endpoint URL in AWS IoT. And it's a really good protocol for IoT because it doesn't require a persistent connection like a WebSocket. So if your device loses connectivity out in the field, as soon as it regains connectivity, it can start sending messages again to that broker. So that's the protocol that AWS IoT uses. And the data formatting that it uses is called JSON, or JavaScript Object Notation. And it's a data format which is really easy for humans to read and for machines to parse. And it's also becoming a bit of a standard in IoT applications. Here you can see an example of a JSON message that's sending some sensor data about a turbine. And it is publishing this to a topic over MQTT. And as you can see, it's pretty straightforward to see what the humidity is, what the output is, things like that. So one of the issues, though, with this publisher-subscriber model is that there's not really a good way of making sure that any control signals that you send is going to arrive in sync to your application. For instance, so if you imagine sending an on-off message to a light, there's no guarantee that it's going to come in to the device in that order. It could just as easily come in as off-off, on-on, and then instead of flickering the light would just be turned on. So I mentioned device shadows earlier, and one of the things that device shadows can get around is that very problem. So the device shadow has two states recorded. A last reported state of the device, as well as a desired state, which you send from your control application. What's more is that each one of these states has a version associated with it. So you know exactly what the last desired state and the last reported state of your device is. The AWS IoT shadow is just a JSON object which has associated special MQTT topics. So there's updated topics, there's a delete topic, there's a get topic, and there's also a delta topic. So a delta topic and a delta value is really just the difference between the desired and the reported state. So you can parse out that delta object and then know exactly what your device needs to do in order to go from its last reported state to its last desired state. So the shadows are really the core way of communicating to a device and making sure that it's behaving in the way that you expect it to. So that's kind of AWS IoT in a nutshell. There's a lot more to kind of learn and dive into it, but for now, hopefully you guys get a good overall idea. So now that we've talked about the basics, I kind of want to dive into something that has just been released recently, and it's called AWS Greengrass. So despite of all the benefits of MQTT, and despite the fact that shadows help you alleviate some of those issues, there's still going to be some problems using a cloud-based compute model. For instance, if you're depending on the cloud compute to control, let's say, a factory, and the internet drops out to some, weather phenomenon, let's say blowing out a power line somewhere, your factory would be left without a means of controlling itself. There could also be issues with latency. So AWS is a massive system, and it has servers all over the world. And while usually it operates with a negligible amount of latency, if your control system has very high timing requirements, even 50 or 100 millisecond latency can become a huge problem. And, lastly, there's also sometimes just too much data, too much raw data to send out in any kind of efficient way. So let's say that you encounter one of or a few of these issues, but you don't want to give up the scalable as-a-service model of cloud computing completely. Well, what can you do? The fog. And yes, that's what we are actually calling it these days. Fog computing was a term coined by Cisco, and it refers to bringing some of the critical components of cloud computing down to the edge, or in our case, down to the NUC gateway. So this allows a system to do real-time control without worrying about latency or intermittent connections, but still retain a connection to the cloud. This fog system also maintains the same data structures as well as the same APIs as the cloud that it's based on, so you can quickly scale your processes up to the cloud or down to the edge, depending on any kind of changing requirements. And the AWS service Greengrass is Amazon's implementation of this fog compute idea. So AWS Greengrass takes three main elements from AWS IoT, the shadows, the MQTT broker, and the SSL certificate security. And it also packages AWS Lambda and runs these services locally on the gateway. So I discussed the first three elements earlier, but I didn't really talk about Lambda much. What Lambda does is allow you to run code in the cloud without having to provision an entire virtual machine to do so. Basically, it's a runtime environment right now for Node.js, Python, Java, and C Sharp, which launches your function at specific triggers. For instance, you can call a Lambda function to do some processing on some incoming sensor data using that rules engine that I mentioned earlier. So all four of these services run on a Greengrass core. In order to create a Greengrass core, you have to install the Greengrass agent on your device. And this agent establishes a communication line to your AWS Greengrass service running in the cloud. Then by using the AWS console or the CLI, you can configure your Greengrass core. Basically, what devices are going to be connected to the core, what Lambda functions are going to be running on it, and where the data is going to go using subscriptions, as well as obviously those certificates that I mentioned earlier. And once you configure your core, you can deploy it to your device using this agent. So once you have deployed your Greengrass core, you can connect devices to it over either the local area network or any other means that the device has to connect. So USB, Bluetooth, things like that. So for instance, if you're running a smart home system using Greengrass, you would have the core running on a NUC gateway, which is connected to the internet via your router. Then you would connect your smart thermostat, your smart doorbell, and let's say a smart toaster to the gateway over either a local area network, if those devices have connectivity, or any other interface that they might have. So each one of these devices is going to be assigned a certificate by Greengrass in order to ensure that only authorized devices can communicate to the core. And the core is going to maintain a device shadow state for that thermostat, that doorbell, and the toaster. And it's going to handle all the local control using a Lambda function. So the core maintains a device shadow for the thermostat, the doorbell, and the toaster, and then does all the local control via a Lambda function. However, the core also sends and receives periodic messages from AWS IoT so that the user can check the temperature of their home or tell the toaster to warm up a frozen waffle as they're driving home. Once all of this framework is set up, what does it actually do for the end user? Let's just kind of take a step back and see what we've created here. So by deploying the Greengrass core locally, we're able to run any control systems in real time without having to worry about latency, drop connection, or data size. Obviously, we're also going to want to be able to send that data and control the device by connecting to that Greengrass core from AWS IoT. But also, since Greengrass uses the same APIs and the same data structure as AWS IoT, we are also able to scale very easily from that edge compute model to the cloud compute model very quickly, depending on our business needs. So we're able to provision our Greengrass core, the functions, and the subscriptions in the cloud, and then deploy it remotely to our devices. We can also do any sort of updates to our deployments and monitor the overall health of our devices. And finally, we can do all these things securely with authentication happening at every step, from the device to the core to the cloud. So in conclusion, what I want you guys to take away from this presentation is the following. The Intel Commercial IoT Developer Kit and our developer program allows you to quickly prototype industrial IoT applications by giving you access to all the hardware, all the libraries, and all the code samples to do so. And by utilizing Amazon's Greengrass technology alongside that, you are then able to take that IoT application and create a secure and scalable fog solution, which combines the power of AWS IoT with the power of local compute on Intel hardware. So finally, I just want to show you guys how all of this works using a simple demo. Before we dive into the demo, let's just do a kind of a high-level overview of what we're going to be showing. So at the core, we have the Intel NUC that's running a Greengrass core. And our device in this case is going to be an Arduino 101 that has a button connected to it. When that button is pressed, the Greengrass core updates the shadow state on the device and then sends a message to AWS IoT. So while that sounds pretty simple, there's a little bit more that goes into it. And let's take a closer look here at what protocols we're using and how the data is actually going from point to point. So when that button is pressed, it's going to send a signal to the Arduino using a GPIO. It basically sets a pin to low when it's pressed. The Arduino passes on that message about the pin going low to the gateway using Emre and Fermata, like I mentioned earlier, to a Python script that's running on the gateway. When that script detects a button press, it publishes a message to the local Greengrass broker topic, in this case, /button, using MQTT. There's a local Lambda function listening to messages sent to that topic based off of our subscriptions or a rules engine that was set up for this Greengrass core in particular. When a message is published to that /button topic, the Lambda function passes that message to AWS IoT using the device SDK over MQTT. The Lambda function also updates the thing shadow with a reported state of how many times the button has been pressed. And once again, it uses this using the device SDK and MQTT. Okay, well, let's check out how this works. Okay, so first of all, let's SSH onto our NUC gateway. We're using the default user, NUC user, and the default password of root. This is definitely something that you will want to change before you deploy your device in the field. Let's take a look at that Python script. And this script is going to be the one that's responsible for listening to button presses and then publishing to that local Greengrass topic. So at the top, we are importing Emre and the UPM libraries, which we're going to use to connect to Arduino 101 and then read button presses. To send messages to the Greengrass core, we are using the AWS IoT Python SDK, which we also import into our script. So here we connect to our local MQTT topic of button. And we also want to make sure that the local MQTT broker is running on the Greengrass core at the local IP address of our device. We provide certificates that were generated by AWS IoT to secure the connection here. And then we create a simple hello from Greengrass message and encode it into a JSON object. Finally, we wait for our button.value, which is the high-level UPM call, to equal 1. And then we will send our messages to that Greengrass core topic. And that's it for this script. The rest of it is going to be handled by the subscriptions and by the Lambda functions provisioned for this Greengrass core. Now, I kind of want to take a look at AWS IoT. So we log into the console, go to the IoT dashboard, and here you can see the connections, the messages, and the general information about your IoT deployments. Let's go to the Greengrass group. Here we are using the Intel AWS workshop group that was created earlier. And we can see the deployment status and the deployment history of this group. It looks like it's still up and running. Let's take a quick look at the cores attached to this group. There's only one core here, the Intel AWS Workshop core, and let's take a look at it for some of its properties. Here you can see that there is a Amazon resource name, or ARN, which is really useful to connect the core to other AWS services. We can also see the shadow state of this core, and basically we've assigned it a color, which can either be reported as green or red. I mean, pretty simple, but you can see how the shadow can be used to track the state of your core. There's also some metadata here, timestamp and a version number. We can also see that the RESTful API endpoint is here under Interact. So we can also see the RESTful API endpoint here, as well as information about the local endpoint here. Next, let's take a look at the devices associated with our core. So each device is going to have an ARN, a shadow, an endpoint, as well as certificate security, just like the core that we looked at earlier. Next, let's take a look at the Lambda function that we have running on our core. We can open it up in AWS Lambda to take a look at the actual code. As you can see, this code is written in Python, and it's pretty simple. We import a few libraries and connect to our IoT data topic with the Greengrass SDK. All that our function really does here is when triggered by the subscription, it's going to republish the incoming message to our button cloud topic. And this is a topic that exists in AWS IoT, not the local Greengrass core. Next, I kind of want to take a look at some of the settings for our Greengrass core. So we're going to go back to the console here and check out the settings. So we can see information about policies associated with the core, essentially permissions that we've given this core to talk to other AWS services. We also see the certificates that we've associated with this core, as well as when they will expire. This is a good place to check on the health of your core security. Okay, so that's basically the overview of what's happening in the cloud. And let's kind of take a look at it in action. So we're going to go back to that Nook terminal and launch our button script. Once launched, we can click the button attached to our Arduino 101, and we should see a message published response. Okay, great. So basically, this means that the button press is being read by the Python script, and it is publishing a message to the local Greengrass topic. Now, to make sure that the subscription and the Lambda function that we provisioned is also functioning properly, let's go back to the AWS IoT console, and we're going to pull up the MQTT clients. We're going to subscribe to all topics, and we are going to monitor these topics for incoming messages from our Greengrass core. So here we can see the messages are coming in. So what this means is that our Greengrass framework is functioning as expected. Now, if it wasn't functioning as expected, there would be a few ways that we can debug it. One of which is checking in our shadow topics under update rejected. And so basically what this topic is created especially for sending rejected messages to the shadow update, which will basically give you an idea if there's any kind of errors happening. There's also something called CloudWatch, which logs all of your generated logs from your services. but here it's working fine, so I'm not going to really go into that too much, but there's plenty of documentation out there for it. And that's Greengrass and Intel IoT in action. Okay, well, I hope you guys have enjoyed taking this look at, both a new service from Amazon called Greengrass, as well as a fairly new idea in the IoT world of fog computing. And I hope you kind of have a better idea of both where Intel lies in the ecosystem and as well as what you can use AWS IoT services for. Once again, my name has been Martin Kronberg, and I'll see you guys next time. Thank you very much.